All right, welcome everyone. In today's lesson, we're going to see the calculus of power series. So specifically, we're going to see how to differentiate a power series. Next time, we'll see how to integrate a power series. But we'll see the main idea today. And then we'll also see how we can use this idea of differentiation and integration to help us express or represent a given function as a power series. All right, so let's get to the main result. And here it is. And basically what this says is, well, if we have a function and it's defined by a power series, and that power series has some radius of convergence r greater than 0, well, that function behaves surprisingly nice. So the function that's defined by that power series is continuous, meaning its graph doesn't have any jumps, holes, or breaks in it. The function that's defined by that power series is differentiable, so we can calculate its derivative. And that function that's defined by the power series is integrable, so we can actually calculate the antiderivative. We can integrate this thing. So it's pretty surprising. We know with series and power series, there can be lots of issues with convergence and divergence, but they behave surprisingly nice. A function that's defined by a power series is continuous, it's differentiable, and it's integrable. Now we have to kind of specify where all this happens. And this all happens on the interval from a minus r to a plus r, where r is the radius of convergence and a is the center point for our power series. And so what this interval represents, let's make a little note of this. This is the interior of our interval of convergence. So we know, what do we mean by interior? Well, it's everything in between the endpoints. So we know that there's questions about what happens at the endpoints for our power series. And for this result, sometimes there can be issues at those endpoints. So we're just going to focus our attention on everything on the interior, everything inside our interval of convergence. There might be issues, there might be things that go wrong at the endpoints. But in between those endpoints, everything in between, perfectly fine. Our function is guaranteed to be continuous. We can differentiate it all we want, and we can integrate it. All right. So how we actually calculate the derivative and how we calculate the integration, we'll see this written out, but it's a process that we call term-by-term differentiation, term-by-term integration. So just a note here, when we differentiate or integrate a power series, the resulting power series has the exact same radius of convergence. Like we said, with the interval of convergence, things might change at the endpoints. So we're primarily going to be just considering this on the inside, the interior of our interval of convergence, because there can be potential issues at the endpoints. All right, so let's see how to actually calculate the derivative and calculate the integration. So let's say we start with a function, f of x, and it's defined by a power series. And here we've written out the first few terms, and then we also have the sigma notation version. All right, so what is it? This function is our coefficient c0 plus c1 times x minus a plus c2 times x minus a squared. Again, a is the center point for our, kind of the center of our power series. In sigma notation, we're doing the sum from n equals 0 to infinity of our coefficient c sub n times x minus a raised to the n. And we want to differentiate this function. So let's see what term-by-term differentiation looks like. So if we were going to calculate the derivative, let's do it. That would give us f prime And what's C0? Well, that's just a constant. So the derivative of a constant is 0. So derivative of that first term is nothing. It's 0. Now let's go to the second term here. We're going to differentiate this. So we have C1 times x minus a. Derivative of this is C1. So that's the derivative of the second term. Now we go to our next term, C2 times x minus a squared. We differentiate this. So we're going to do general power rule. So bring down the 2, put it in front. And then keep what we have inside exactly the same, x minus a. Subtract 1 in the exponent, so we go from 2 down to 1. And then the derivative of the x minus a, derivative of the interior piece, or of the inner term, is 1. So we're just going through, and essentially we're differentiating each term individually. It's just a power function, so we're just using power rules. The power rule, or the general power rule, to differentiate each of these. Let's do one more. Let's differentiate this C3 term. What would it look like? Well, when we differentiate, x is our variable, so we bring down the 3, put it in front, so 3 times C3. Keep what we have inside the parentheses exactly the same, x minus a. Subtract 1 from the exponent, so we're down to power of 2. And then normally with general power rule, we'd be multiplying by the derivative of what's inside the parentheses. So kind of like a chain rule here. But derivative of x minus a is just 1. So we're not going to really include that. And that process continues. So essentially what we're doing for differentiation is we're just going through and differentiating term by term. And you can see we're getting a new power series here. Now what does it look like with the sigma notation? Well, sigma notation is we're going to differentiate what we have in here. So it'll be Cn times x minus a to the n. So essentially when we differentiate a power series, we're just differentiating our general term here and adding up the results. Now one thing to note is that when we differentiate, I wrote it wrong here. Well, I was going to say intentionally, but I wrote it wrong. This is going to be n equals 1. And that's because when we differentiate the, I mean, it's not technically wrong, but when we differentiate the n equals 0 term, we get 0. So just a little note here about our starting index when we differentiate. When we differentiate our starting index, or when we differentiate our power series, that first term, the n equals 0 term, is going to just differentiate to 0. And we saw that right here. So the n equals 0 term is just a constant. Differentiate a constant, we get 0. So the starting index may change when we differentiate. All right, so that's differentiation. Let's see what integration looks like, term by term integration. So we're going to calculate the integral of f of x dx, find the antiderivative. And what we're going to do is the same idea. We're just going to go through each term and just integrate it. So we know with integration, we always add on a plus c, so we'll put that at the beginning this time. Now let's integrate this first term, c0. So when we integrate that, we're going to introduce powers of x minus a. So if you want, you could almost think of this like a substitution, a u substitution type integration. but we're going to introduce powers of x minus a so that it matches up with everything else here. So that would be the integral of this first term. Now what would be the antiderivative of that second term? Well, it would be 1/2 times c1 x minus a squared. So just power rule for integration. What would be the integral for the next term? Well, it would be 1/3 c2 times x minus a cubed. So essentially what we're doing is Essentially what we're doing here is we're taking the power function x minus a and just doing power rule. So we add 1 to the exponent, takes us up to 3. Take that new exponent, flip it, put it in front. So that's how we're getting the 1/3 in front. And then the coefficient is just a constant, so that just stays the same. And we just keep doing this. So we're just going term by term. And actually, let's get one more in here. So we have our C3 term here. So the power function is x minus a cubed. So when we add 1 to the exponent, we're going to get 4. So we'll put a 1/4 in front. Then we have our C3 coefficient. And then power rule. So we're adding 1, x minus a to the power 4. And that continues. And what that looks like is essentially what we have is when we do the integration here, we have the sum from n equals 0 to infinity of the integral of our So essentially what we're doing is to integrate this function, what we do is we just integrate each term of our power series. It looks like this. So the integral of cn times x minus a raised to the n dx. And we're doing the sum from n equals 0 to infinity. And we know that here we don't have an issue with the starting index because we actually get more terms in. And to really emphasize the fact that we have a plus c here, maybe we could even put a plus c in front, like that. All right, so this is the general process. Let's see it in action. So let's look at it, example 1. We're given a power series here. It's defined, we have a function defined as a power series. So f of x is equal to the sum from n equals 0 to infinity of x to the power n over 2n factorial. And to see how this differentiation process works for an actual example, let's write out the first few terms here. So when n is 0, we're going to get 1. And then when n is 1, we get x over 2 factorial. And then we'll have x squared over 6 factorial, or 4 factorial rather. And then x cubed over 6 factorial, and maybe one more. X to the 4th over 8 factorial. And this keeps going. All right, so let's calculate the derivative of this. So we're going to differentiate. And let's start by first just differentiating each of these terms for our power series. So let's actually hold off on the sigma here, especially that starting index. Again, I did it again, wrote n equals 0, but let's see what's going to happen. So let's look at our starting terms here. We have n equals 0, n equals 1, n equals 2. We've wrote up to n equals 4 here. Wrote out the first 5 terms. Let's see what happens when we differentiate. So that n equals 0 term is a constant. When we differentiate, it's gone. Then we differentiate the next term. Derivative of x is 1. So we end up with 1 over 2 factorial. Let's go to the next term. Derivative of x squared is 2x. So I end up with 2x over 4 factorial. Keep going. We're just going term by term. So what's the derivative of x cubed? It's not too bad. It's 3x squared. And 6 factorial is just a constant. And then the last one, derivative of x to the 4. What's the derivative of that? Well, it's 4x cubed. And then all over 8 factorial. So what happens here is when we differentiate, that n equals 0 term is just a constant, so it's gone. It gets killed off in the differentiation. But we still have an n equals 1 term, n equals 2 term, n equals 3 term, and so on. So we're actually going to start our summation here from n equals 1. And then what does the actual derivative here in sigma notation look like? Well, we really just differentiate this. So we bring down the n, keep x the same, subtract 1 in the exponents. We're just doing power rule there. And then this is all over 2n factorial. And there we go. So if we have the terms written out, we just go term by term and differentiate. If we have it written in sigma notation, well, we just differentiate the general term. Now, the one thing to note here is we've looked at this power series before, and this power series we saw has a radius of convergence of infinity. So this actually converged for all x values. So what that means for our purposes here when we're talking about the derivative is this brand new power series that we have also has the exact same radius of convergence. So let's just make a note of that. F prime of x, well, the radius of convergence for f prime of x is the same. So r equals infinity. And that's because when our previous result said that the radius of convergence when we differentiate doesn't change. So our original function here had a radius of convergence, and our derivative has the exact same radius of convergence. So another way to think of an infinite radius of convergence is the power series converges for all x values. So there's really no endpoints to worry about on our interval. So we could think of it the same way for f prime. So f prime, this brand new power series, is going to converge for all x values. All right, so differentiating a power series is not too bad, and it preserves a lot of the work that we would normally do. So finding the radius of convergence, if we differentiate, it's going to be the exact same radius of convergence. So that's kind of nice. All right, we're going to use this idea of differentiating a power series and integrating a power series. We can use that to kind of broaden the scope of what functions we can represent as a power series. So there's going to be more functions now that we can represent as a power series, and the idea is to start with our function and then differentiate or integrate it so that we get something similar to our prototype form that we looked at in the last lesson. And so let's just kind of review that result really quick. We have this 1 over 1 minus x, and we can write that function as a power series, so 1 plus x squared, and so on. Or it's the sum from n equals 0 to infinity of x to the power n. Really, this is a special case of the geometric series, where the r value here is, the absolute value of it is less than 1. And we've looked at this We've seen the interval of convergence is the open interval from -1 to 1, and then the radius of convergence is r equals 1. All right, so the idea is we can try to relate a given function back to something that looks like this prototype. So let's see an example. Let's look at example 2. We're given a function, f of x equal to 1 over 1 minus 2x squared. And what we're going to do is we're going to find a power series representation for this function by kind of relating it back to that prototype. And the idea here is we start with our function. And we want to make this, we can kind of see it looks like that prototype, 1 over 1 minus x. The only difference here is this squared. So if we could integrate this function, if we actually integrate this function, what do we get? We would get 1/2 times 1 over 1 minus 2x. So if we were to actually integrate this function, we would get 1/2 times 1 over 1 minus 2x. And this 1 over 1 minus 2x is very similar to that our main prototype form that we kind of rely on to find these power series representations. So the idea here is we start with our function and we can integrate it to get it in a more recognizable form. And then what we're going to do is we're actually going to find a power series representation for this function, because we actually know how to do this one. So let's actually find the power series representation for this. And we're really going to focus in on this 1 over 1 minus 2x. So let's just remember, 1 over 1 minus x, what is that? It's the sum from n equals 0 to infinity of x to the power n. And what we're going to do is we're going to, for our specific case here, the value that we're going to plug in is we're plugging in 2x. So we're going to plug in r equal to 2x. So wherever we see an x here, we're actually going to change that to a 2x. So when we do that, let's keep the 1/2 in front. That's just a constant multiple, so we're just going to keep that in front. And then let's write down the power series. It'll be the sum from n equals 0 to infinity. And if we plug a 2x into here, so wherever we see an x, change it to a 2x. And that's going to give us a power series representation for 1 over 1 minus 2x. We're going to have the sum of 2x raised to the power n. And let's simplify this down a little bit. So we can split up the power. So it'll be 2 to the n times x to the n. And then we can bring this 1/2 inside. It's just a constant multiple, so we can bring it inside the summation. And then when we do that, we can multiply it with this 2 so that it'll actually decrease the exponent. So it'll be 2 raised to the n minus 1, and then x raised to the n. All right, so what we've done is we started with our function. This was the function we're interested in. We actually integrated it to get something that's more recognizable for our kind of our general form here. We were actually able to find a power series representation for this. That's great, but it really doesn't answer the question. So to get back, we have to kind of undo the process. And we differentiate. So we started with our function. We integrated to get this more recognizable form. We found the power series representation for that more recognizable form. But we have to undo that integration. So the way to undo it is with differentiation. So let's differentiate this power series. And when we do that, we're just going to go term by term. We know that n equals 0 term is just going to end up being 0. So we're going to start our sum at n equals 1 now. And let's differentiate. And this 2 to the n minus 1, that's just a constant. So when we differentiate, we're going to take the exponent, which is n, bring it down, put it in front. Again, the power of 2 is just a constant, so that's going to stay the same. And then we subtract 1 in the exponent on our x term. So just power rule. So we differentiate that x to the n. And that's really what we're doing. So bring down the n. So we get n times x raised to the n minus 1. And maybe to make it look a little nicer, put the n in front. Still has to be inside the summation, though. So this is an n, so we can't move it in front or anything like that. All right, so here's our power series representation. So this is pretty good. We're able to find a power series representation for this function. Now, we also want to find, well, let's write that out. Now, we also want to find the radius of convergence. So what would the radius of convergence be? And we're going to consider, let's consider the radius of convergence for the power series that we started with. And if we can find the radius of convergence for this power series, well, then the radius of convergence for this one has to be exactly the same. Because when we differentiate a power series, it doesn't change the radius of convergence. So if we can find the radius of convergence for this power series, well then, because we differentiated, the actual power series that we're interested in has to have the same radius of convergence. So let's figure that out. So we have this power series 1/2 n equals 0 to infinity of 2x to the n. And this is a geometric series with a constant multiple in front, but that constant multiple is not going to do anything. So this converges when the absolute value of that geometric part, the 2x, that kind of the r value there, is less than 1. So the absolute value of 2x is less than 1. 2 is a positive constant, so this is true if and only if 2 times the absolute value of x is less than 1. And then solve for the absolute value of x term. So this statement's true if and only if the absolute value of x is less than 1/2. And that's actually our radius of convergence. So when you get the absolute value x term all by itself, the number on the other side, that's your radius of convergence. So in this case, r is equal to 1/2. So what that means for our purposes is the power series that we're actually interested in, which was the sum from n equals 1 to infinity of 2 raised to the n times 2 raised to the n minus 1 times x raised to the n minus 1. The radius of convergence for this power series has to be exactly the same. So r is equal to 1/2, just the same. All right, so this is kind of a little strategy that we can use to kind of expand the types of functions that we can find a power series representation for. So just to kind of go through this process, let's just look at it one more time. We started with the function we were interested in. It wasn't quite our usual format. The usual format is 1 over 1 minus x. Really, it was this squared that was causing an issue. So what did we do? Well, we integrated to get a more recognizable form. From here, this form, we're actually able to use this result to actually get a power series representation. But this isn't our answer because it's a power series representation for this antiderivative. That's not quite what we want. So we want to undo this integration. Let's differentiate the power series now to get the one we actually want. So we start with our function integrate. We get this more recognizable form. We find the power series. And then to go back, we have to undo the integration, so we differentiate. And now we have a nice power series representation for this form that we necessarily wouldn't be able to do. And then knowing what the radius of convergence is for this easier power series allows us to quickly say what the radius of convergence is for its derivative. All right, so next time we're going to see how to integrate a power series, and then we'll see an example where we kind of do something very similar to this, except we have to integrate a power series. All right, so we'll see you then. Bye-bye.